For practice 2, we are going to run a one-way repeated measures ANOVA. The description of our data are going to be for the spreadsheet labeled practice 2 in your activity dataset. And we have a researcher wants to know how similar VO2 max estimates are for 3 different protocols. VO2 max in milliliters of oxygen per kilogram per minute was measured during each protocol for 27 healthy individuals. The order that the protocols were performed in were randomized for each subject across 3 data collection sessions. Each session was 1 week apart. So just based off of the first sentence here, you should be able to notice that what we are measuring is VO2 max. Another giveaway is that units have been provided, which indicates that it is a parametric type variable or quantitative in nature. The other thing you should be able to pick out from that first sentence is that or the researcher really, is looking at the differences between 3 protocols. Each subject performs all 3 protocols. Right? As we said, they perform them in 3 different data collection sessions. So that's what tells us that protocols is a within subject independent variable. In the spreadsheet, we are going to organize our data such that we can run a one-way repeated measures ANOVA, since this study design is appropriate for this type of test, since we have one dependent variable that is ratio data. We've got one within subject independent variable that is nominal data with at least 3 levels. We are going to assume that our VO2 max data are normally distributed with no significant outliers, so that kind of checks off another assumption. And we're also going to assume that we're running a 2-tailed test with a 95% level of confidence, which should be the default in SPSS. After we run our ANOVA, we'll go ahead and interpret the results. So I'll walk you through how to read the output. And then we are going to create a bar graph that represents the mean differences between protocols. So very similar stuff to what we did last week with independent ANOVAs. Additionally, in here, it's in your answer sheet, but we are also going to calculate the omega squared effect size. If you need to reference the equation that I'm using, it is in the Module 8, Part 2A PowerPoint on slide 22. I think it's literally the last slide in the PowerPoint. But for any of the procedures that I'm running through, if you want a picture example, instead of going through with the video, you can always just use the entire Module 8, Part 2A PowerPoint. With that being said, let's go over to our data set. So we can see we've got our 27 subjects in the first column. And then we have our VO2 max values for Protocol 1, for Protocol 2, and for Protocol 3. When we think about how we're going to put our data into SPSS, for repeated measures, each measure should have its own variable, or should have its own column. So we identified our independent variable as protocol. That means each protocol should have its own column. Each row should have 3 values in it. Right? So each subject or rows in SPSS represent subjects, and each subject was measured 3 times. So if you set up your data, you have in SPSS, you cross-check, go through a list of things that need to happen. Does each row have the number of times that every participant was measured? If not, then your data is set up incorrectly. Okay. So the way that we have it set up right now should be fine to stick right into SPSS. I'm not going to copy the subject number since SPSS in the data view already has the rows labeled as subject numbers. I do want to copy the protocol labels though. So I'll copy that, and then we'll go into SPSS, paste our data in, In the variable view, just make sure that all of your measures are scale. This should be the default, but just in case, change them over. To run a one-way repeated measures ANOVA, we go to Analyze, General Linear Model, and Repeated Measures. Under the within subject factor name, that's where we're going to put a general name for the independent variable. In this case, protocol is a perfect naming label. We have 3 protocols total, so that's the number of levels. And then we can add that into our within subject factor box. The measure that we have taken is VO2, and I'm going to capitalize that. We can add that to our measure box, and then click Define. This will then pull up the repeated measures dialog box, which is where we're going to run all of our calculations and set everything up for our output. In the within subject variables box, you'll notice that protocol is in parentheses. So that indicates that 1, 2, and 3 are the 3 levels of our independent variable that we specified in the previous dialog box. VO2 is just indicating that this is the dependent variable that each of these protocol levels go to. So because our protocols are already organized in 1, 2, 3 order, we can just highlight all of these and insert them into our within subjects variables box. We then need to set up our post hoc test or our pairwise comparison, so we'll click on the EM means button, insert protocol into display means for, and then we will compare our main effects using a Bonferroni adjustment. So this is setting up our post hoc tests or pairwise comparisons. The last thing we do is set up descriptive statistics and estimates of effect size. This options box is also where you set your significance level. So because we are at 95%, our alpha level is 0.05. So again, that is the default for SPSS. We can then click Continue and OK, and then we get an output. So I'm going to label mine practice 2. So I don't lose it, because every single one of your tests this week is going to show up as general linear model. I'm going to take out the notes because we don't need those. At the top of the output, you'll see the within subject factors. So if you ever forget your labeling method, you can always go to this first table, and that will tell you which variable is associated with which protocol number. Our descriptive statistics are then listed in the table under that. As we scroll down, you will see a table for multivariate tests. We don't need this, so I'm going to take it out of the output. After that, we see Mauchly's test of sphericity, which is where we look for the p-value for our assumption of sphericity. We don't get to check this before we set up the test. It's automatically included in the analysis. So we can see our within subject independent variable protocol, our Mauchly's test statistics, and then our p-value for sphericity. What we have here is a p-value greater than 0.05. So that indicates that we should accept the null hypothesis for our assumption, generally meaning that we have met the assumption. So the interpretation or the null hypothesis for sphericity in this particular case is that the variances of the differences of each level of protocol, or all the levels of our protocol, are relatively equal. Okay, so the variances of the differences of all the levels of protocols are equal. When we have assumed sphericity, we then can go to our test of subjects, or test of within subjects effects. So this is our main ANOVA table. And next to protocol, we can see we've got various options. Since we assume sphericity, we will stick with reading this row. And we get the p-value for our main effect of our ANOVA. So in this case, p is less than 0.001, which would indicate that there's at least one significant difference between the protocols with regards to VO2 max. So you could phrase it that way. You could also say that protocol has a significant effect on VO2 max, right? There's a lot of different ways that I've presented it to you guys so far, but that's the p-value for the main effect of the ANOVA and the interpretation of that main effect. The next table in the output is tests of within subject contrasts. We don't use this, so I'm going to cut that out. The test of between subjects effects we will not use this week, but we will use it next week. So I'm going to cut that out for now as well. And then the next thing we end up seeing are the estimated marginal means section, which is our post hoc tests. So we'll direct our attention to the pairwise comparisons table. We see that protocol is listed by number, and we have our pairs listed here in our table. From this, and I didn't show you guys this last week because I actually just learned how to do it, but if it helps when you're, transferring your answers back and forth from your output to your answer sheet, if you double click in the table and you choose, like, I've identified a significant difference between protocol 1 and protocol 2, you can click on that cell, and then there's an option to highlight that particular cell. So you know that you've already accounted for the difference between 1 and 2. We also have a significant difference between protocol 1 and 3. So I'll highlight that cell as well. I've already accounted for the difference between protocols 1 and 2. I have not accounted for the difference between protocols 2 and 3. However, this p-value is greater than 0.05, which indicates that protocol 2 is not significantly different from protocol 3. So when I'm listing my significant pairs, I now have them highlighted in my table, and I could phrase it like all protocols are significantly different from each other, except for protocols 2 and 3. Or you could also say protocol 1 is significantly different from protocols 2 and 3. But protocol 2 is not significantly different from protocol 3. Okay? So I phrased the question, I think, so you're listing the significant pairs only. There are several ways you can word that. I'll leave that up to you. All right. So that's pretty much it for our one-way ANOVA analysis in SPSS. The next thing we are going to do is calculate the effect size. So we'll come back to our spreadsheet, and I'll make a section for effect size. To calculate effect size, we need some pieces of information. So this will be my variable list. I need a K, I need an F, and I need N. In this instance, K is representing the number of levels of the independent variable. F is the F statistic from the ANOVA table. N is going to be the number of subjects. Okay. So once we know what each of these variables represents, we can find them in their respective places. K being the number of levels of our independent variable, we already know is 3. The F statistic from our ANOVA table we can get from our output. So I'll go back to our test of within subjects effects. We had used sphericity assumed, or the rho for sphericity assumed, and the F statistic associated with that table is 47.249. So we'll put that in here. And then we had 27 subjects total. For my omega squared, it's really a curly W, but regular English W is as close as we're going to get. We have, well, put equal so that you can start putting in your calculations. And I'll give you guys two options on how to do this. You can either type everything in which case I would start with parentheses divided by parentheses, so you're separating your numerator from your denominator. The other way that you could do this is you have a numerator calculation and a denominator calculation, because there are several sets of parentheses that could start getting mixed up if you just try to type it all out at once. So I'm going to do the split way first. In the numerator, we do k minus 1, so the number of levels, minus 1, times f minus 1. And that's it. The denominator is going to be exactly the same, so k minus 1 times f minus 1, and then we add the product of n times k. Then to get our effect size, or our omega squared, we just divide the two of those cells. So the numerator divided by the denominator. I specify your guys' reporting to 3 decimal places, so we'll do 0.533, which easily is greater than 0.14, so we know we have a large effect size for the differences between our protocols for VO2 max measurements. Okay. So this is kind of like the split way we can calculate effect size. If you wanted to calculate effect size just straight, I would recommend doing equals parentheses divided by parentheses. In your top parentheses, you would have 2 parentheses in which you're doing k minus 1. Outside of those red parentheses, you're multiplying another set of parentheses with f minus 1. We then repeat those steps. So I have 2 sets of parentheses, one where we have k minus 1, and the other one we have f minus 1. Still in this second set of black parentheses, we then add the product of n times k. And I press enter, and we should get the same answer that we had when we split everything up. Sometimes I find students like it this way better, just because it's more of a stepwise process. You have less error with your parentheses. Whoops, I didn't mean to do that. But in either case, 0.533 is going to be our omega squared effect size. So I'll just highlight that in yellow so it stands out. The next thing we were supposed to do in SPSS is create a bar graph that represents the mean differences between our protocols. So the easiest way I know how to do this, or I can think of how to do this, is just to create mean and standard deviation calculations under each column of our protocols. So we do these using our regular average and STDEV formulas in Excel. I will reduce these down to 2 decimal places, and we can copy our equations across the columns. From there, to get our bar graph, I can highlight my data labels as protocol, and then I can press and hold Command if you're on a Mac or Control if you're on a Windows computer, and that will allow you to multi-select your means for each of your groups. From there we go to Insert, and then we choose our column graph. And then you guys can come up with a chart title like VO2 max values in different protocols, in 3 different protocols. I don't know. Personal preference, I like to reduce my y-axis values down to nice whole numbers. So sometimes it's nice to have decimal places, but in this situation, I don't know. Right? We definitely need axis labels, so we'll add a primary horizontal, which is more of a condition type label. So this is the protocol, and then our y-axis label would be representing our, I'm going to move my cursor, sorry, representing VO2 max with the units of milliliters of oxygen per kilogram per minute. Similar to last week, I like it when the groups are different because they just stand out better. So I will change mine to orange and green. Sure. The last thing we have to add on our bar graph are the error bars, which are going to be based on the standard deviations that we calculated for each group. So we go to Add Chart Elements, Error Bars, and more error bar options. We then can go to this kind of 3-bar error bar options, both directions custom. And then we can specify our positive and our negative error values to match the standard deviations that we calculated for each of our protocols. Once we press OK, our graph should auto reformat. And this looks about right because all of our means of our protocols were fairly similar and all of the standard deviations were fairly similar. So this would be your graph. Again, make sure you add a chart title, but this would pretty much cover all of the components that you would need to have for the graph to be ready to copy and paste into your answer sheet. That pretty much does it for practice 2, and I'll see you in the next video for practice 3.